All right. So yeah, this is Rust for Rustaceans by Jon Gjengset, Chapter 3, Designing Interfaces. Forgive me if I'm rusty on my Rust. Haha. That might be the case. Yeah, if you want to chip in, go ahead. I don't mind. Yeah, and let's crack on. Oh, all right. So as we start reading the Chapter 3, straight away we are thrown into the statement that projects, they do have an API. Oftentimes it's just the user-facing API provided by HTTP or CLI, but also you have something called the developer-facing API, right? And this is really what we are going to be focusing on today and over the Chapter 3. Oftentimes it's a very strict API, which is a library or crate public API. But it might be as well your internal crate within the crate API. And as we are talking Rust, we are going to be talking Rust-specific things, namely types, traits, and the module boundaries. So there are basic rules as for creating APIs, and basically the APIs should be unsurprising, they should be flexible, they should be obvious, and they should be constrained. And weirdly enough, in that part of the book, Jon mentioned straight away the references that he tells us to go at the end of a chapter, but I decided to mention them here as well, not at the end of the book. And these are Rust API guidelines, really good guidelines. Then you should be using Cargo Clippy. There is also RFC for API evolution and the Cargo book Semver compatibility chapter. And it looks like deliberately, he didn't mention that in the book, but I think it deliberately, he just chose few things for just chunk of these API guidelines that he's talking on in the book. And that's why he's basically saying for the rest of them, just go into these resources. Yeah, so we said there are 4 characteristics of the APIs. So let's go into the first one, unsurprising APIs, right? And basically that means that the API should follow the principle of the least surprise. And that holds to naming practices. That also means the traits or the type should be implemented into common traits. That also means the traits should be pretty ergonomic, and we should be using wrapper types wherever they should be used. If it comes to the naming practices, we basically should be following the naming and behavior practices, right? And what that means is that if the user sees somewhere in the code a function called iter, what they do expect, because they are coming from the Rust world, is that they expect something that resembles the iterator function or function on the iterator type, which is basically the one taking a reference to self and returning the iterator. And likewise, if they see somewhere in the code into iter, what they are expecting is that to behave as the into iter implementation that consumes the self and it returns an iterator, right? So basically, whatever with the naming and the behavior of those things that are named, we should be following what is in the standard library and in the mostly known crates. Similarly, if it comes to types, if I see somewhere in the code in my crate that I have a struct that is called something error, straight away I would be thinking it should be implementing an error trait, right, with the description function. Yeah, and then if I'm creating some kind of an API, let's say a crate, then I'm gonna be creating types there, and all these types, they really should be following something, the rules that make them just work. And basically that means I should be implementing very well-known traits for these types for them to just work. And this is specifically important because our users, they won't be, because of the coherence rules, they won't be able to extend my types with some foreign traits. So really, it's on us to be implementing those traits for our types and be providing them the functionality of those. And it's even more important that we will see that later, but we should be thinking about those traits upfront. That's why we're going to be going through the list of those important traits. And the types should be implementing as many as possible of those important traits, because later on, if users start using our crate with the current definition and implementation of traits on those types, and if they start using it and we start adding some kind of implementations, then we might be breaking backwards compatibility with the users, and they're not going to be happy about that. So yeah, the first trait that is basically like one of the most important traits to be implemented is just the debug trait. And it is because of the matter of how the software engineering works, right? We need to print stuff out to decide if it works, if something works or not. And basically, Jon in his book mentions that do implement debug no matter what, even if it's just mentioning the name without inspecting and without the description of whatever it holds internally. And of course, most of the time we can just derive debug, which basically for us as the creators is a simple thing to do. But if there needs to be some kind of customization, we would just implement the debug for our type. And potentially we would be using some helper functions on the formatter that are provided to us. Then the second thing that he says about the traits for the types that we're going to be providing is that we should not be disabling send or sync auto traits, so the marker traits. And if we do, and we should have really an important reason to do so, and if we do so, then we should really document that so that the users are aware of it, right? And why it is so important is that if something doesn't implement the send trait, then it cannot be placed in the mutex, and basically it cannot be used even transitively in anything threaded related. And that also means in any asynchronous code, because our asynchronous code is most of the time executed somewhere on the thread pool. And also, if the type doesn't implement the sync trait, then it cannot be shared through arg, or it cannot be even put on the static variable, which somehow I didn't think of before. All right, then we're moving to the next traits that are pretty important. So the clone and default. Reason for them to be important is that most of the time our users want to work with more instances of types, of our types. So they want to create them with the default values or clone them. And if we don't implement them, again, do document the reason for not providing clone and the default. Implementing default, we can just derive it or implement the default for our type. Same for the clone. Yeah. And then the next type we should be implementing is the partial equation. And the reason for implementing that is it's not that difficult, first of all. And the second of all, there is going to be a time when our users will want to compare values for our types. And the partial EQ should be at least implementing the instances, right? So, for instance, that comes handy in the case of tests. If we're if we want to compare values, then that is needed. The way of implementing that, again, we can just derive, or we can use some more or some more complicated logic to specify the equation. Like in this example, even though the book has a format and ISBN number, right? We only define the partial equation to be on the ISBN number. Yeah, and then we are moving to more traits, the partial order and the hash. And I'm not really sure why he mentioned that the partial order should be implemented if we are, because so he says that we would be, they would be useful, especially in the collections. And I've had a look at the traits needed for the collections in standard collections, right? And basically it's order, it's not the partial order, but that's what he says in the book, basically. So again, we can derive, and important thing about the partial about the partial order when we're deriving is that it has lexicographic top to bottom members order, right? And then if we want to implement hash, then we obviously want to implement EQ and then the partial EQ as well. And the hash is important, for instance, if we want to use our types as the keys for sets, hash maps, things like that. Then the question is, what should be about the EQ and OR traits? And the agreement basically is that, yeah, we can implement them, but we should really be careful, and we should really make sure that they, the EQ and ORD, which are much more strict, that they really apply to our types. And like the example is that, for instance, you would not be able to implement the EQ trait for floating pointers, because, for instance, not a number is not equal to not a number. And yet another thing about the common traits to be implemented for types is the traits from a third-party packages, specifically in what he mentioned is the serde trait. So to implement the serialize and deserialize. And obviously, if we just simply implement those traits, we are going to introduce a dependency on the third trait for all our dependents, so our downstream packages that are going to be using us. And he's basically suggesting that we should be in our TOML, we should add a feature for serde, right? And only if users choose the feature serde, then we would be going to the block that conditionally compiles the serde traits for our types. So there is also a question about the copy trait. And what Jon says is that users usually don't expect copy to be implemented on the traits. And it's even contrary. We shouldn't be implementing that because it's too easy to make mistakes and think that we are moving things instead, but we would be copying them. And the other thing is that if we implemented the copy trait for our type, it's easy to lose the copy because for a type to stop being copyable. And that means we would introduce the backward incompatibility. So really think hard if you want to have a copy trait for the type. Yeah, and then we're basically moving to some more information about the traits. So we already had the collection of the traits that we should be implementing. Like in the API documentation, there are even more traits, but I guess those are the most important that Jon thinks should be implemented on any type. So the other thing is, obviously, we are implementing the traits for our types for our API to be easy to use. But even though we've implemented those traits, Rust is not automatically implementing traits for refs of the types that implement the traits. So for instance, if we have like a printable trait, and we have some kind of a structure that implements that printable trait. And if we want to use it, then we would be able to use it normally here, right? But then if we try to use it via the ref, so the compiler is gonna complain for us. And the same for mutable ref, right? So basically what Jon says in his book is that we should implement a blanket implementations for printable. So for our traits, blanket implementation for printable for any type, for a reference to any type that implements the printable, and then also for the mutable for any type that implements the mutable. And he also says that it's not done automatically because depending on the use cases, you might not want, for instance, to have some of those traits implemented, right? So it's probably a good default, but still think that maybe you shouldn't be providing some of those. Yeah, the other thing about ergonomicity of traits implementation is that if we have something that we should be able to iterate over, then it's normal thing in Rust ecosystem to be able to iterate over it. Like for instance, so here example is about a vector, right? But if we had some kind of container that contains elements, we should be providing ways of generate iterators, right? So we should be implementing into iterator. Then also we might want to iterate over references or mutable references. So we should be also implementing those for the references and mutable references, basically. Then oftentimes when we're talking about the types, we in Rust we have wrapper types, which wraps around some other types just to give them extra functionality, and those are called wrapper types. Oftentimes, smart pointers are the wrapper types. Right, and in case especially for smart pointers, which is basically a transparent wrapper types, we should be thinking about implementing the deref trait. And the reason is because it's giving us magical properties, right? And basically those magical properties are that when we call a method on the wrapper that implements deref, we are eventually calling method on the inner type. And the deref, so the compiler is can do something called implicit deref coercion with functions and methods, which basically helps us not to write boilerplated code. And just to present it, we've covered that with the Rust book, right? But just to present it, if we have types that are wrapping around each other, so string internally it holds string, it holds something that can be eventually reference to the string slice, right? Then if we wrap the string into the box, so box and string, they do implement deref types. Then if we want to invoke a function on the string slice only, then we don't really have to be dereferencing box to get the string reference, to dereference it to get the string slice. We can just use this, and our compiler, it will know what to do, and it will get the boilerplating for us, done for us. The worth mentioning thing is that when we are implementing the deref, we should not be implementing any function on our wrapper type, like this here, right? And the reason is that we don't know what kind of type we're going to be wrapping around. And if that type happens to have the same function, or function similarly called as the function we implemented on our wrapper type, then we might get into the collision that we won't be able to tell, or we won't be able to call the function of our destination type. So basically what is being mentioned is that we should not be doing this, implementing inherent functions on the wrapper type. We should be having static functions that are taking a reference to the wrapper type. And then with such an approach, we would be able to call one or the other. Sorry for, yeah. Okay, the next tip that Jon is giving in case of just unsurprising APIs and easy to use APIs is that if we have a wrapper type and it has and access to the inner type is not slow and it doesn't have any complex logic, we should implement just as ref because it provides a cheap way of getting a reference to another type, the inner type. And also it gives it gives us much more flexibility in terms of where we can use this particular type. So it's like this, right? Asref is for string slice, and it's also asref is implemented for a string, and we can just pass it to the generic function that takes as reference. So it's just a good approach, right? The other thing about the wrapper types is that Jon says that we should probably implement the from inner type, and he also says into inner type. But then everywhere else in the API design guidelines, it said we shouldn't be really be implementing into, because if we implement from, we will have blanket implementations that give us into implementations. So that's why I just crossed it out. And basically those from into, they are giving us easy access of adding and removing wrapping from the wrapper types. Again, just example is if we have a struct of a password that really holds a string inside it, either we can get from string into the password, or we can get from the password to string. And with those easy implementations, we can have niceties like saying, get me a password from a string, and then just saying password into a string variable. Yeah. Yeah, and I think the last thing that he mentions is that for these wrapper types, we should be really we should be hitting straight away the borrow implementation of the borrow trait, and it is because it's very unlike the dref and asref, and it's intended only for the types that are for the wrappers, or to implement the traits for the types of the wrappers that really are equivalent to the inner types. Whereas the dref and asref, they basically act as can act as. Yeah, borrow also, it has some blanket implementations for references, and it does require that the hash, eq, and or traits are exactly the same on the wrapper type and on the inner type. So basically the statement from him is you don't have to worry about that. All right, then, so we've covered the unsurprising APIs. So now we can go into the flexible APIs. And what does that mean is that when we are talking about the API, right, our code is a contract, and this contract consists of requirements, and the requirements are restrictions on how our code can be used. But our code is also given promises, which are guarantees on how our code can be used and how it behaves, right? If it goes to the requirements, we should be avoiding unnecessary restrictions. We'll come to why. And if it comes to our promises, we should be making promises on only the promises we can keep. Again, if it comes to the requirements, we should, whenever we add some restrictions, so we should be worried about that, then the same version, then it's a backward incompatible change, because clients that are using our code, now they might not be compiling anymore. Whereas if it comes to the promises, so our return types, for instance, when we are removing some promises, again, this is how we break our contract, and that is backward incompatible change. However, on the requirement side, if we relax some restrictions on our input functions, let's say, attributes, then it's just a change that is not breaking any usages. And for the promises, if we are giving extra promises, that's fine, because the currently using codes, clients, customers, users, they only worry at that particular point in time about the promises that we've already given. And in Rust, requirements, they are specified basically as a trait bounds and argument types, whereas promises, they're specified by trait implementations and the return types. And in this point in time, in book, Jon is giving us just a nice narrative about these kind of three functions. That basically what each of them, what it does is it takes a string and it returns a string after some kind of processing. So they look very alike, but they are very different if it comes to the flexibility of the API. So for instance, the first function is it needs a caller to own a string, and it's also moving the ownership of a string to itself. So that's that requirement on the calling code. But it also says that it's gonna return an owned string, which basically means it will have to make an allocation inside the function, and which also means if we ever use this function in some code, we won't be able to use allocation-free code anymore, right? It's a little bit better, if you can use that word, right, with the second function, because it doesn't require anymore the ownership of that string, and anything that can deref to the slice can be acceptable by this function. Potentially, you still need to, on the calling side, do that dereference. And then it gives us some kind of flexibility saying, if there is a logic that can return non-owned string, then I will return that. Otherwise, I will create, I will allocate another string, right? So this is much better in terms of performance, let's say. But still, if we wanted to have a better implementation of the string, we wouldn't be able to, right? And then there is this third version of the function, which is very generic. And the genericity means that you have lots of freedom of calling it and lots of freedom of consuming that the result of that function. So basically, from even this description above, right, we can see that the generic arguments, if it comes to the flexible API, is something that we want potentially to have, because they allow much more types to be used when the function is being called. So we're talking about arguments at the moment, right? So and again, this is an example, right? This is much more generic and it accepts many more types than this function. And the rule of thumb is that do make arguments generic if you can think that some other types, if you can think of other types that can be used when calling the function. Obviously, once the functions are generic, they have some problems, right? So there is a catch always about it. There might be a monomorphization bloat. Obviously, you can tackle it with the dynamic dispatch, as we've known from the chapter 2. But then once you say, oh, I'm going to be using this function, but on the dynamic dispatch, at this moment, you are taking away from our user the freedom of deciding if it should be a dynamic dispatch or just a monomorphization. And of course, because it's a dynamic dispatch, it might have some performance problems if you're using, for instance, that particular function on a hot path in a loop, let's say, right? Yeah, so user cannot opt out anymore if we as the creators of the API, if we decided that it will be utilizing a dynamic dispatch. And yet another problem with this approach is that when we decide to take trait objects, then we cannot have complex trait bounds like a combination of few traits. If we look from the other side, so if we decided not to go that way of generifying the arguments, and if we basically said, let's start with the concrete arguments of our functions. So let's say this is our API, and we use it like so. It might occur to us that later on, if on the version 2 of our API, if we decide that, yeah, we want to generify that function because we are going to be using, or our customers are using many more types, and we want to get that flexibility of the API. And if we change it, for instance, to that second version, we would realize that some of the usages already of the code like this are not compiling anymore, because previously the compiler could infer the destination type, and now it cannot infer that anymore, right? So by us going the other way, we might be breaking backwards compatibility with the code of existing customers. And that's important to keep in mind. If it comes to the object safety, so object safety is something that we should be thinking of when we're creating APIs. So when we creating our traits, just because we can be using the dynamic trait thing. But still, don't stress too much. First, think if you want to keep your trait object safe, right? And we are being given examples that, for instance, the from iterator, it doesn't make sense to be object safe for this trait to be object safe, because it, for instance, none of the methods is taking self on it. For instance, the other trait seek, it's useless on its own, just seeking, right? Whereas the drop trait, yes, definitely you want to keep that. So our creators of Rust standard library, they do want to keep it object safe, because it is a valid thing to, for instance, be allowing for deferred dropping and then be using the then drop, right? And again, if we ever want to be changing object safety, this is a backwards incompatible change. Just to remind ourselves why we might want to have the object safety, right? Is that if we have different types that implement our object safe trait, then we might put them into one container, for instance, with a dynamic trait reference, and then we might want to invoke. We would be able to homogeneously invoke that trait methods on it with the dynamic dispatch, right? So it's just giving us a much nicer ability of working with types. So there are ways on involuntarily we might make our trait non-object safe. So for instance, if we're adding methods with generic arguments, or if we're returning self. In the first case, for instance, there are ways again of preventing that trait from not becoming object safe by, for instance, going with our generic arguments to the trait type, or maybe annotating, putting that onto those particular methods, which would make those methods not available for dynamic trait actions, but still the trait itself would be kept object safe. And then with the flexible API, we are being moved to borrowed versus owned dilemma. And basically, Jon says that whenever we're talking about function, trait, or type, we need to think of the member data that we are that we hold inside them. So should they be owned, or should we just have references to that data? And definitely impacts ergonomics and the performance of the code, right? So what he says later is that, for instance, if the code needs the data to be owned, we do want to make our caller aware of it. So we shouldn't be taking that data by a reference and then cloning inside our function. We should be explicitly telling to the user that they need to allocate the data, and we are going to be moving it. And obviously, if the code doesn't need to own the data, we do want to tell them that we're going to be working on the data with the references. And to that particular rule, right, there are exceptions for the small types, because like integers, because it doesn't make sense, or it's as expensive to copy the reference as a pointer as expensive it is to copy themselves, right? And again, he says that we should be careful about the types that implement copy, like, for instance, the vectors or slices. And there are some exceptions to these rules, obviously. So there are types that are conditionally that have conditional ownership, like the code type. And also the exception is that if we're making our function too complicated for the user to use because of us handling that borrowed and owner the way how we think is the most performant, sometimes we just might break those rules and get a nicer interface for a user with the catch of paying for a performance, let's say, right? Then he's moving to the destructors. And obviously, when we're working on the code, we need to have some cleanup, right? So we are allocating resources, we are allocating memory resources, we are allocating connections, whatever, right? All of this is a resource. And then we want to release it at some point, right? And the natural place to release the resources is the destructor. In case of Rust, destructor is basically the drop type, or is defined by the drop type, right? But the problem with the destructor is that with the drop type is that if they fail, those destructors, we don't have access to the information why they failed and what's the reason for that. And yeah, the only way of basically handling it would be to panic, but that's not a good idea to panic from those destructors, right? Pretty the same thing as for C++, basically. And well, what he says that basically what we should be going for if we are worried about those potentially lost resources and non-cleaned resources is that we should go with the two things combined. One of them is to do the best effort with the drop trait implementation, and then also to add an explicit destructor on the type and document that. And the explicit constructor can be called by our users who want to know about those potential problems while cleaning up. And they wouldn't be calling them if they don't care. So then the drop implementation would worry about cleaning up. Yeah, just one thing is that on the explicit constructor, again, for the usability of the API, we should have a consuming self, right? Reason being is that once we close, once we distract, we shouldn't be able to use the particular type. All right, and this is just one of the examples, and you can see that this example would not work, right? Of how that looks in almost production. So basically, we would implement that explicit destructor function. Then we would also, for a structure, we would also implement a drop type for a structure that would want to call this explicit destructor, but there are problems, right? So the drop trait drop function takes mutable reference, but as we said, we want to have a consumable interface. And then the other thing is that if the drop trait would be called anyway, and that might be having problems because we would originally be, so if we called close explicitly, potentially we would move some resources already, but then, or we would move some data out already, and then the destructor would be called, and that could have some unwanted the bad things could happen, right? So there are workarounds around that, and I didn't put that as an example because they are much more complicated, right? So then to get this thing going or working is that you might implement the new type wrapper. So you would have an inner around the option inside our outer type. You would be taking the inner in both destructors. But then the disadvantage is that you would have to delegate all the functions on the inner type from the outer type. The other thing is that you might split all the fields into takeables, and that would work if the takeables have same empty default empty values, and it soon gets tedious. Or then you can also have a manually dropped on inner that is also takeable, but then this is unsafe, right? And then the whole problem with all of this is that the code itself, even though it might be doing simple things, it's just getting complicated, right? All right, and the other thing is that from what we said about the APIs is that our APIs should be obvious, right? And the fact is that our users won't know all interfaces, rules, and limitations. So we basically need to make our interfaces easy to understand and hard to use them incorrectly. And that is basically done by our types and special naming, like function name dangerous. So the users would reach out to, so based on types and on special namings, they hopefully would be aware that something is strange, and they would then reach out to the documentation, right? So the obvious API is basically achieved by providing a good documentation. And the good documentation means you document cases where code doesn't unexpected things like panics or returns errors or has some unsafe functions and provides then the color required guarantees. The good documentation also has end-to-end examples because many of us are just learning by doing. And we're talking about end-to-end examples at crate level and at the module level. And then also we should be able to organize our documentation, so to modularize it, to have links between each modules so that it's nice to navigate. And we should not be afraid of using doc hidden, doc alias, and doc config just to give some more information. So to hide unwanted the documentation part that we don't want to show to the user, to enable searchability, and to provide user information that particular part of the documentation is based on the config. Then obviously it's good to link to some external resources that we were implementing our code on. And then the other part of the obvious API is the type system guidance, right? So this thing is basically using our types. So Rust is strongly typed language to enforce some kind of behavior on the way of how our users are writing code. And this is enforced by the compiler. And basically, there are a few ways of doing that. One of them is semantic typing, which basically instead of when we're calling functions, for instance, instead of just using Boolean values, we would be giving them enums, and then users won't be able to mess them up, and it would be much more readable. It also works for different structs when we want to carry information about units, for instance. And the other example that he's given is to use zero size types to indicate facts about an instance of a type. And basically that means that we are he's implementing with marker structs, which are zero-sized types. He's implementing a state machine of the rocket containing a stage that is basically that points to the phantom data to that zero size structure. And then with that approach, we can enforce on our users the way how they are interacting with the whole state machine, right? So basically, they can only do things that we allow them by those type implementations. I won't be discussing that much further because we are running out of time, I guess. Then he's also saying that another part of it is that we might use the must use annotation, but this is nightly. And that one basically says if we can annotate it with a type. So if we're creating a type, it needs to be assigned somewhere and used. Otherwise, we're getting warnings from the compiler. Same for the functions. If we annotate it with must use, then the return value of it needs to be used as well, right? And then the last part of our APIs is the constraint API part and basically what that means is that once our crate is there out for a while, our users, they start to rely on our API, and that basically means if we make changes to the user visible changes, we might break things, and obviously there are some things that are obvious of breaking, and then we as creators we can be aware of it. But there are also some subtle things that we need to keep an eye on, not to break backward compatibility unintentionally, right? And he's giving basically a few of the examples. But first of all, he gives also a rule that we should really make public only what we really need to be public, because users otherwise are going to be depending on things that we didn't want to. And then breaking compatibility with a big surface of code is much easier to do than with just narrow subset of the code, right? Yeah, and he gives few examples of the changes that unexpectedly can break compatibility. And basically, for instance, one of them is that if, let's say, we have a structure, the unit, and it's being somewhere used in the user code like that. And then if we add a private member to that unit, we potentially could think that it's private, so it's not exposed to the user. So everything should be fine, but really that means we just broke the constructor that they were using, and that means backward incompatibility, right? Similarly, again, with adding a private field to the structure, is that when they are using, so when we had our version 1.0 of a library, and we had a public field on the unit, somewhere they in the code they were doing matching somewhere. And then we added another field to our unit. That means now this matching code is broken because it's not exhaustive. And that particular thing for both of those examples, it can be fixed or worked around with annotating our structures with non-exhaustive, which basically, first of all, wouldn't allow to use implicit constructors. and then it wouldn't allow to have matching in the user code that is not using exhaustive pattern matching, right? So always those two dots, they would have to be added in the user code, which means the code would still compile, not necessarily it will be the code that is doing the correct things, right? The other things that might be breaking our user code when we are making changes to trait implementations in our crate is that when we are adding blanket implementations to our code, that might break some functionality on the user. When we're adding implementations of foreign traits for our existing types, when we're adding implementation of existing traits for foreign types, and all of those are backward incompatible changes, right? However, implementing traits for new types is okay because our users, they didn't have access to the new types. We just created them. But still, it's breaking if we implement existing trait for existing types because those users, they might have so they didn't implement our trait to our type, but for instance, they might have implemented their trait with a function that corresponds to our create trait function. And even though in our version 1.0 of the library, we were not implementing, let's say, this trait, so they were able to implement their trait and be calling foo on the type, on our type. Then if in the version 2.0, we implemented that foo1 trait on our type, then that is basically breaking because it is causing ambiguity. So basically, when we have trait implementations, the breaking changes are changing signature to any functions on the trait. That not only breaks the implementations, so any traits, any types that are implementing our traits, they are breaking because now they need to adapt their implemented functions, but also the clients are getting broken because they need to change the way how they're calling trait functions. But when we're adding a method to already existing traits, we only break implementations because the clients, they were not calling those methods. Those methods were just added. We would break implementations of those traits unless we provided a default implementation. But potentially it can cause some ambiguities, right? But because of that, this that we are seeing here is that if we were able to make traits that cannot be implemented by that cannot be implemented by foreign types, few of those things, so adding methods and changes signatures, they would, or adding methods, sorry, they would not be breaking, they wouldn't be causing breaking changes. So if you're thinking in the future, right, and you think that you have some traits and you might be expanding those traits and you still want to keep the backward compatibility, you might want to make your traits sealable with the disadvantage of people not being able to implement them, but this is what you want to do, right? Yes, so still, if you do that, do document it. And last but not least, I think, is that there are some hidden contracts on our interfaces. And basically, the hidden contracts are if you have a contract elsewhere. So if our crate is pulling some other crates, and if we are exporting types of that crate, then if we change implementation detail, right? So if we change the version of that crate that we depend on, we are going to be breaking implementation of our customers. So we are making a backward incompatible change because from the Rust perspective, or basically the types provided by that by that external crate, they are not compatible anymore. Even though they might have the same structure, it's just being better safe than sorry on the Rust compiler. And we can mitigate that by just wrapping those foreign types in the new types and not basically not exposing them in our API. There is also a SM version trick. I won't go into details with that because we run out of time, right? And then the last thing is that some traits obviously are automatically added by the Rust compiler to our types. And those traits are sensing. We have discussed them. We do want to keep them most of the time on our crate types. There is also unpin sized, unpin save, and what the other ones. But they are added automatically until they're not, right? And the problem with that until they're not is that if, for instance, we have a type A which we expose to our customers, our users, that contains type B, and for some reason type B stops being sent, then also A stop being send transitively, and that is a super breaking change, right, for our customers. So basically the suggestion by Jon is just to add some test functions. So if we know that we want to test our types, we are exposing to the customers, and we want to test that they are keeping the compatibility and they're keeping the trait bounds, then this is a nice trick to have them. Nothing is running this code. It's just if it passes the compilation, that means the trait still has these characteristics. Okay, and yeah, this is it. I didn't put the end QA slide, whatever.
Awesome, thanks, Krzysztof. That was great. We'll open to the floor for questions. Stunned silence.
I actually I'm wondering like about the deref trait, because it's so convenient to use it, but I also think you shouldn't overuse it. So what are your experiences with it? When would you use it? Maybe
I think the Rust book is giving the rule saying use deref only for smart pointers type.
Mm-hmm. But that's a bit very restrictive, right?
Yeah,
because
yeah.
I have nice use cases in mind, and I just remembered this rule and just wanted to question it now.
I guess never forget you have into as well. So
maybe like this example with the rocket, it was quite short, but you know where the slide is with the rocket and the market type? This is when this would be not only a toy example, maybe you would have like some data field there too, like a data structure. And then it would be quite, yeah.
You can have data, right? And you can move. You can use move semantics, right, to move the data around from one type to the other. Mm-hmm. So that wouldn't be also very costly. I'm just thinking, how can I? Because yeah, now I don't know how to get to it. Oh my gosh. Oh, I thought I put the link there. No, I put the link there.
Well, I'm still using PowerPoint, but I think this is much more cool.
So this example, right? It was cut out on the slide, to be honest, but easily Rocket can have some stage values here, right? It's not really a problem. And then like probably you could think of maybe those should maybe those don't need to be. So if the state is different for different if the data is different for different states that the rocket is in, then maybe the data should be really on the structures, these discriminative structures, right?
Mhm.
But if the data is always shared, then it would be put here. But that's not it is a toy example, but it can be easily done here, right? You would just declare the data of whatever type, and you would just be passing in there, right? Provided that the data is movable.
Right, that's true. Like I was just thinking, when you have like now several states and like this data structure, you could just spare this dot data if you need to access an internal data for some reasons, because like there are two goals. Like you want to restrict the interface with having different states or internal states, but maybe you really have just shared data, because a rocket probably has the same data if it's on the ground
I mean,
than in the sky.
we say it's shared state, but this is one instance of a rocket, right? So it's one state per one instance, or sorry, it's one data per one instance, right? It's not shared state between any of them. It's just because we are creating different rocket types, right? Just to constrain usability of the API, we are going to be moving that data from one to the other, but we're not sharing it. We're just moving it between the types.
Yeah, that's true. Maybe shared wasn't the best word. Like I just was thinking of having an easy access to the data. So that was something what really Deriv would do, right?
You can put the data in the grounded and launched structures.
Yeah,
right?
yeah. So
and you can implement methods for that on their specialized implementations.
So this is what I tried to say, right? If the data, potentially there is a core data that is the same for whatever state the rocket is in, right? That's what my data would be here, right?
Mhm.
But if there is like the particular data that can be only in the grounded state or launch state, I would make I would put it here, right?
Yeah. So what I have
and you would have a field then based on stage. So you could have stage underscore data colon stage inside the rocket.
Yeah. Then
and you wouldn't need the phantom data.
Anymore.
You wouldn't need the phantom data at that point.
And you already know inside that particular state, you already know that the stage. I don't know why they called it stage. For me, it's state, to be honest, right? But the state is of a ground type within these implementations, right? Within this implementation, the self.stage is of a launch type, right? So yeah, obviously, it is a toy example, right? I guess. So if it's a flat state machine, it's probably okay. But if you have like nested state machines, I didn't think of how it would really look like.
This isn't meant to be a state machine. This is meant to restrict the interface based.
But it is a state machine at the same time, isn't
it? Kind of, but it's really you should think of it as making sure that you don't do call accelerate before launch. And to basically to enforce a sequence on how you use the API.
I've seen people do a similar thing with like authentication. So like you can authenticate a user with different types, and then you can use you use the phantom data there, because there is no data associated with that beyond just the user data, but you can still strongly type it so that you can only pass authenticated users to certain methods by attaching a level of authentication equivalent.
However, I think Krzysztof has a point. Like you really have underlying this finite state machine there, right? Where you say like I have like the states rounded and launched, and for both of them, there are different interfaces. And there's also some special methods like launch that is like in a finite state machine, the transition.
I think there are two wins here, right? And basically, this is limiting the usage of API, not to be used incorrectly. And there is also that it's giving you a nice state machine implementation.
There is an implicit state machine there in the type. The state machine's in the type system rather than in any code.
Yeah.
So you can map a graph showing the different stages. The first one being grounded, and then there's a transition to launched, and so on, right? And you can have more complex graphs if you wanted to, based on it. So for example, you can have a network that's unconnected and connected, and so with unconnected, you might have some connect functions, which gives you an unconnected thing, which may have more information and more APIs, but you can still have I've seen this done in C++ as well.
Yeah. It's just with C++, it's much more verbose code, right? That's the problem.
I've also used generics like this to for like mass libraries where you want to associate a coordinate space when you do a matrix multiplication. So you can make sure that you can only add two vectors that if they belong to the same space, like screen space or object space or whatever. And when you do a multiplication of a matrix will have two spaces associated with it, the starting space and the end space that you transform into. And so you can only multiply vertices of one space to produce a vertex of another space by only using the matrix that covers those two spaces, right? So it's just you're encoding the semantics in the type system, and it's a very powerful thing. We should get it right. No, I don't think anyone else has done that. That's the thing I did, but I haven't seen anyone else do it.
I'm curious now, Matt. Like in C++, it's like a lot of code, right? Like I'm thinking of this template traits things that you have to come up for this, or how? Like I just for the talk I will give next week, I prepared a bit in this direction for the type state pattern, and I had the feeling in C++ you have to be much more verbose.
Yeah, that is definite.
I actually found a library for C++20, I think, that supports the type state pattern like it is used in the Rust ecosystem.
There are so even the boost units, right? And I remember I listened to one of the podcasts with the guy who created this the library for for physical units. Also, I think Bjarne, C++ language, right? I think he even has an example there about how to be implementing those kilometers, meters, right, and whatnot. To have them safe, right? So it is doable. It's just lots of boilerplate in C++. It's much nicer in Rust.
Do we have any more questions? If not, I will steal the screen share to talk about what's coming up.
Thanks for the talk, by the way. It was really good. There's lot of stuff to.
Yeah, it was lots of it. Oh my gosh, it took so much.
It's a deceptively
short chapter. It was a long chapter.